Okay.
Hello, everybody. Very good. My name's Tom. I'm Tom Wilkie from Grafana Labs.
And I am Bryan Boreham from Weaveworks.
We work on a project called Cortex. So who was here for the intro? It stopped working. Oh, there we go. Who was here for the intro talk? We were? We were. Oh, wow. I was expecting more people. OK. What do you reckon? Should we change the talk?
I think it's most of them.
So, OK. So who runs Prometheus, then? Who's here? Most of you. Good. And who's already familiar with Cortex, considering this is the deep dive? OK, good. Well, we'll do a bit of an intro before we get in. It's only a 30-minute talk, so what we thought we'd do is just focus on one particular piece of Cortex. So we're going to do a bit of an intro, we'll do a bit of a demo, and then the main deep dive is going to be about Cortex's query path. In the past year or so, we've done a huge amount of work on making it really fast, and that's why it's awesome. So I'll do the brief intro. Yeah, this is not working very well. So Cortex is a time series database. It's a horizontally scalable, highly available, what's the fourth one? Long-term storage for Prometheus. So it's got a Prometheus-compatible API. You use Prometheus to send samples to Cortex, and then from there, you can scale it to as much as you like, pretty much. It's a CNCF project. It's on GitHub. It's all Apache licensed. You might ask, why did we implement it like this? Why has it got these features? What's interesting about that? We've done 4 use cases we've tried to address. So what we really want to see, a bit that's kind of missing from the Prometheus world, is this idea of getting a global picture of all of your metrics. If you're running multiple clusters, maybe geographically distributed, you're going to have to put a Prometheus in each one of them, and then you need a way of getting a big picture. So there are a few ways of doing this. You can federate your Prometheuses. You can use Thanos, or you can use Cortex. So they're the kind of 3. There was a talk earlier from the Uber guys doing M3. Very similar use case. The second one is we want a different story to high availability. In the Prometheus world, you run a pair of Promethei, and if one of them fails, you kind of have a second one. But in most worlds, this it tends to lead to inconsistent results or gaps in the graph. We wanted a different story. We wanted no gaps. And we wanted to put a bit more time and effort into using more modern consistency and high availability techniques. So we basically do replication. We wanted to offer long-term storage. When we started this project 3 years ago, Prometheus had a bit naive storage engine, that was very practical, but wasn't potentially that advanced. Since then, Prometheus 2.0 has a much better storage engine. You can put long-term data in Prometheus. Don't let anyone tell you otherwise. But we wanted to offer a different trade-off. We wanted something that was a bit more durable. We wanted something with a bit more replication. We also wanted to take advantage of cloud storage. So we wanted to have Cortex basically write its data to Bigtable, DynamoDB, GCS, that kind of thing, S3, that kind of thing. And then finally, we originally started the project at a company called Weaveworks, which Bryan works for. When we originally started that, we wanted to offer Prometheus as a service. We wanted to sell this so that people could send their data and have someone else worry about the storage side of things. To do that, we wanted to make the system multi-tenant. So what we really didn't want to do is have to run a new Cortex or a new Prometheus for every new customer we got. And so we wanted it to be multi-tenant. What this means is a single Cortex cluster can manage kind of isolated Prometheus instances within the cluster. Every job fundamentally understands every request is for a given user. Are you trying to sit down, Bryan? You're supposed to be here.
I noticed people needing a seat, so I thought I'd free one up there.
OK, good. So
please.
Yeah, so that's really that's the introduction to Prometheus, really, to Cortex. Really super straightforward, what it is, what it's for. If you have more questions about how we achieve some of this stuff, the intro talk goes into a few more details. The README on GitHub has links to 3 years' worth of presentations and talks that talk about the algorithms and the design and architecture and so on. Really what I want to do now, about half of you are here for the intro, and I didn't have enough time to finish my demo, so I just want to show you Cortex. I want to run it and show you how to use it. And then we'll get into some more interesting stuff. Well, this will be interesting, I hope. So, gather windows. Do you want to provide a running commentary?
Well, there's nothing on your... Oh, it says demo time. OK, right.
Right then.
So
can we all see my screen? Oh, we're not going to show that.
So Tom is going to run Cortex on his laptop. He's just going to run it in Docker containers. You know, in production, we tend to run in big clusters using Kubernetes, but for the purpose of firing up a small demo, he's going to run Docker containers.
So can everyone see that? Is that big enough? You can see, hopefully you can see there's nothing up my sleeves. There's no Docker containers running. And so I'm just going to run, first I'm going to run a console node. I've typed these commands in before, so I'm just searching for, there we go. So Cortex needs somewhere to put kind of coordination data to decide which Cortex instance owns which bit of data effectively. So we use console. There's a PR open to use etcd as well. And eventually I want to really do gossip to kind of get rid of this dependency. But it's not too hard to run a single console. The state of the data that's stored in that console is kind of not super important. You can afford to lose it, so you don't have to back it up, for instance. Anyway, so now we have a console. I'm going to turn my brightness up so I can see it. I'm now going to run, I'm going to set the replication factor. So Cortex is configured via a config file. In the config file, you can specify, well, this is relatively new, actually. It was previously configured using command line flags. We've just recently added a config file to make it easier to try and easier to get started with. So I'm going to set the replication factor to 3. Hopefully you can all see that. This will mean that every bit of the data that's written to Cortex is replicated 3 times, or at least 2 times. And then I'm going to Cortex 1. So I've conveniently moved the config file since I typed this command. So we're going to docs. Now, we're creating a container called Cortex1. We're putting it on the Cortex network. This is so it can find the console. We're exposing it on port 9001, telling it to use that config file, telling it to use the Cortex image, telling it to use the config file again, telling it to use that console again. And then log level debug, because when I tried the demo yesterday, it didn't work. Hopefully it does today. So there is now 2. And I'm just going to run that a few more times, calling it Cortex 2. Yep, fingers crossed. Cortex 3.
So this is what kubectl run minus replicas equals 3 does.
Yeah, pretty much.
You could have Tom come around to your data center and run it.
Right, so they all seem to be running fine. So we've now got a Cortex cluster, and if you don't believe me, let me just close that. Oh no, that's what I wanted. If you don't believe me, we can actually go localhost. 9001 was the Cortex, the port I exposed Cortex on. Now this is a view of that state that we store in console to basically show how much each ingester owns of our distributed hash table. So we've got a little bit of ownership. You've got a little bit of actions. If one of the machines fail, you can delete it, and so on. And hopefully, if we go to every single one of these hosts, we'll see the same data. Yep. This shows that everything's pretty much ready to go. Now we're going to start a Prometheus. I'm just in the Prometheus repo, and I've added to the default Prometheus config, I've just added some remote write config. This tells Prometheus to send every sample it scrapes to this endpoint. So you can see I'm sending it to port 9001, which is the first replica of console. If you're running this in Cortex. If I was running this in production, I'd put a load balancer in front of that, and I'd have that pick the console to send each request to. Cortex. I'd have that pick the Cortex to send every request to. Anyway. So I'm deleting the data, because obviously I've run this demo multiple times, and then I'm running Prometheus. So that seems to be working. And then finally, I'm just going to run a Grafana. So Docker run, port 3000, network Cortex, Grafana. Now, if we go and look in the Grafana I just started, which would be localhost 3000. Everyone knows the password to Grafana, right? It's just admin. No one ever changes it. And this is an empty Grafana, so we're going to add a data source. First, we're going to add the Prometheus that's running on my laptop, because I can never remember in Docker how to do that. I've got a handy little URL here. This demo, well, this is an extension of the demo, but this demo will be written up in the README in Cortex if you want to try it yourself at home. So we're saying connect to Prometheus. Prometheus is port 9090, right? Yep. Hope so. Save and test. That works. Now, we're going to add a Cortex replica, Cortex data source. Again, if you were running this in production, you'd stick a load balancer, Kubernetes service, ELB, whatever you fancy, in front of Cortex. But here I'm just going to point it at, because I'm on Docker and we don't have that kind of thing, I'm just going to point it at Cortex port 9009, which should be the right port. It is. So, Cortex, this is Cortex 1, actually, Cortex 3, because I like to live life dangerously. So Cortex 1 is where the data is being written, and I really want to show you that clustering works. So I'm going to try and read the data from another instance. Cortex 3, 9009. Didn't work. Why didn't it work? 9009 is the port number, isn't it? Let's consult this, because that will tell me. It's supposed to. Ah, here we go. Yeah, of course. Cortex exposes the Prometheus eye under API Prometheus, which is there for various historic reasons. There we go. That works. Now, here we can show that the data's in Prometheus, so we're going to do rate Prometheus head, no, Prometheus TSDB head samples appended total. So this shows you that something is going on in that Prometheus instance. It's reading some samples, not a particularly high load, 25 per second. If we split and show that you can read it from Cortex, yes, we get the same data. So hopefully you followed that. I did it a bit quickly, sorry about that. But we can see that Prometheus is pushing data to that Cortex cluster and replicated it 3 ways, and then we're reading it from one of the nodes. And now, the thing I actually want to show, I'm going to delete one of the nodes and show that it all still works. So docker rm-f cortex 2. I'm not going to delete Cortex 1, because that's where we're writing the data. And I'm not going to delete Cortex 3, because that's where we're reading the data. So deleting Cortex 2, not giving it a chance to leave the ring or do any kind of tidying up. So if we go into here, you'll see that there's a heartbeat being written to console, and that Cortex 2, which I assume is this one, the top one, is not writing at heartbeat anymore. So Cortex has noticed it's gone away. And then if we run this, you'll see that it's still reading and writing. I don't know why it's increased in throughput, but it's still reading and writing. It's still Prometheus is still working, and Cortex is still receiving the data and replicating it. And no one, no user should notice any outage here. So if you were for the earlier talk, you would see me run through a bit earlier bits of that demo, and that's just showing you that we do replication and high availability. Okay, that's the demo.
Thank you, Tom.
Shall we? Do you need the speaker notes?
No, can't read them anyway.
I might just try because I need them.
So I'm going to take over now and talk for a bit about how a little bit more detail of the storage engine of Cortex. So what Tom set up was Cortex receiving samples from Prometheus, and in the demo it was like 25, 30 samples per second. People run Cortex at much bigger scale than that, millions and millions of samples coming in, over time billions. That will be handy, thank you. And we store them all in some kind of storage database. We all subscribe to the view that you should never write your own database.
Agreed.
Right, Tom?
Don't want to do that.
So we use a database like DynamoDB or Cassandra or Bigtable, something like that. So the ingest path, we're getting all these samples in, they're all for different metrics, they've got different labels, they're for different tenants. And over time, we've got billions of them on disk. So the problem I want to talk about is when a query comes in, if you think about it, we have to find the right information on disk using only what's in the query. So that's, I'll walk through exactly how that happens. And then Tom's going to tell us how he made it go faster. And this is doing nothing for me.
Yeah. It'll, click it 3 times, it'll happen once.
You think?
Yeah, go for it.
I do want to use the cat botherer to device. So the have we gone on too far?
Yes, we have.
It clicked eventually. There we go. That's the picture I wanted, and I wanted to point lasers at it because I love lasers. So this is a diagram of the query path of Cortex, and in an earlier state. So it's pretty much Cortex. The project has been going for over 3 years. This is pretty much the original design, and didn't change much until about a year ago. A lot of work has gone in the last year. So as I say, a query comes in, and that's some rate this divided by that times linear predict. Whatever your PromQL query is comes in. We run multiple queryers. That's the whole horizontal scalable idea. So you probably run at least 2 of these for availability. You might run 10 of them. You can run 100 of them if you want. You have some kind of load balancer on the front of that, because we really don't care which one we pick. We just enter one of these queryers. We use Prometheus code to parse the query. We use a lot of Prometheus code. And then we need to go 2 places with the query. The very latest data is in the memory of the ingesters. In the ingest path, it's getting compressed down. We do this extremely powerful compression, and it's held in memory. So we need to go find that data. That's the very latest data. And we go to what we call the chunk store, which is the blobs, which are the basic samples compressed down, and an index to find the right ones. And I'll repeat that the whole trick of this is how do we find the exact right blobs? Given we've got billions of them, we need to find the exact right ones to load up, to pass back to the PromQL engine, which is going to then do the arithmetic on the samples. So there's a query. How do we answer that query? We have an inverted index. So this is a very standard technique in NoSQL databases. The basic idea is that the metric has a name, and we're querying on one label, which is our shipping job, just for example's sake. In the database, we've got this metric, and we've got a bunch of different labels that we've recorded the data under. We've recorded it for different jobs. We've recorded it for different instances. It's some kind of HTTP server, so we've recorded it for different paths. We've recorded the different error codes that came back. And what happens in Cortex is that we start with the metric that you're asking for, and then you ask to narrow it down on a label. So that takes us to this line here. And then we match on, it's this one here, right? Shipping. And that points in the index to a series of time series. The time series then point to the chunks of data. Each chunk is typically like 6 hours of data crushed down to a couple of kilobytes. And that's what we read from the store. So look at that.
I think another thing to add there is you can, just for brevity, we've only had one matcher on this. You can have multiple sets of matchers, and then we'll do an intersection of the lookups in the index.
Yeah, we handle queries of any complexity, which is certainly what my customers use. Just to kind of state that another way, so the query came in, same query I'm talking about. We go to the index row for that particular label. We find shipping. That gives us a set of time series. We look up that time series. We get these chunks, which are effectively time-based, a few K compressed and stored in the store. So now we read those chunks in. Those have the raw samples in the time series, and we hand them back to Prometheus, which does the arithmetic over them. And I'm now going to hand back to Tom, who's going to go into even more detail about how that works.
Thank you, Brian. Does this work? No, it doesn't, does it? So one of the things, the reason we did the demo first is because we wanted to highlight that Cortex does replication. We do three-way replication by default. It's configurable, but by default, it's three-way replication. What this means is you end up with 3 copies of all the chunks in your chunk store. And through various like jitter and failures and rollouts and all these kind of normal noise that happens in your cluster, those chunks aren't going to necessarily align. In fact, you had an interesting stat you were telling me.
Yeah, sometimes they do align. They align about a quarter of the time.
About a quarter of the time they align, but 75% of the time they're subtly different. So the first thing we have to do when answering a query is we have to dedupe. We have to merge these all together into an iterator and dedupe them. Yeah, this is just kind of you trying to visualize how they might not align. Yeah, this is useless. It works, but very slowly. So a lot of text, sorry about that. That's really out of style for me. We tried a bunch of ways of doing this. The obvious way would be to kind of turn these chunks into big slices in Go, then use a merge to kind of merge them all together into even bigger slices. And it turns out that's really fast. It's actually the fastest way we could find to do it. The problem is, these chunks, they might only be a few kilobytes, but you do tend to load millions of them. And then decompressing them all. You know, each sample in a chunk only uses about a byte, but when not in a chunk is like 8, 16, something around
16.
that? 16, yeah, okay. So when you decompress them, you end up with a lot of data. And so this is how Cortex did it, you know, a year or two ago. And it would run out of memory if you ran a big enough query. That's kind of sucks, right? So, I mean, it's obvious the solution is iterators, right? Everyone said the solution is iterators. Obviously, the solution is iterators. So we built iterators. And then the question becomes, how do you detect overlaps between the iterators? So we put all the iterators into a heap, and we pop them off, and then pop the next one off the iterator, and then put it back into the heap. And that used basically constant amount of memory, or very, very small amount of memory. It's just really slow. Like, it's got the same big O complexity, but that popping and pushing from the heap and that constant moving stuff around, we did loads of work optimizing this, but it was really slow. It stopped dooming, it was just slow.
So these are like the different stages that you went through optimizing it?
Yeah. So Gotham, who's not here, one of the other Cortex developers, had an idea that we could quickly scan over the chunks and detect ones that don't overlap and produce really kind of simple, naive iterators for those. And that kind of reduces the iteration problem down to just looking at 3 or 4 different streams of iterators. Still pretty slow, it turns out. And the final solution we ended up with is, instead of just, when you're iterating through a chunk, iterating through a series, instead of just looking at a single sample, look at a batch of samples. And so I think the batch size, we tuned it, like the batch size ended up being 12, not particularly big. But it gets you almost back to doing it with slices, like really, really close, 90% of the speed. But it gets you like 0.1 memory. And I'm really proud of it. Like, I look at the code now and I'm like, oh wow. Like, I really don't understand. I have to revise when I go and fix bugs in that code. And anyone familiar with like database engineering and building query engines, we're very familiar with these techniques. Like, I didn't invent them. We just implemented them in Cortex.
So if anyone tells you that algorithms are only used in interviews?
Yeah, this is like a great interview question, I think. We should use it. So we've seen this diagram, but you see, like, we've now moved on a little bit. We've added some caches in front of our stores. So we added an index cache. This was Gotham again. Added this. The challenge with the index cache was very much that we need the index to be live. You know, it's constantly changing as we're writing more data. So you have to coordinate between the ingesters. When we introduced the index cache, we had to hold chunks in the ingesters for some time period, 15 minutes. And that meant that the index cache entries could be live for 15 minutes, could be fresh for 15 minutes. And you have to keep those two things coordinated, and you have to make sure you do that so that every time you do a query, you're guaranteed to recover the chunks and the entries for all series that match. The chunk mem cache, on the other hand, at least chunks, the minute they hit storage, they're immutable. So the chunk mem cache can hold stuff forever. And all we found now really is that you've got to make sure your chunk mem cache is really big. I think we run hundreds of gigabytes of chunk mem cache in production. And this got pretty good. You know, we were getting there. We're starting to get better performance out of this thing. And this is where it started to get fun. We put out a design doc, had some comments from the community, and we introduced what we call the query front end. And this is where we start doing our own load balancing. Oh yeah, Niraj, it won't work with server meshes here either. So we were talking about how to make Cortex work with service meshes. So now the queriers get told what queries to execute by the query front end. And this gave us an opportunity to also introduce query results caching. So in the queriers, we'll go into a lot more detail about what we do in the query front end. So you can see how the point I'm trying to make really is we cache a lot in Cortex. At every single level, at every opportunity, we will try and cache the result. And this has had huge improvements to performance. So what is the query front end? What does it do? So you get a query. This is the same query we had earlier because consistency is good. And first
Eventual consistency.
No, fully consistent. So the first thing we do is we align the start and end of the queries with the step. So in Prometheus, you provide a start and end and a step. And like the step might be 30 seconds, and it'll effectively tell you how many data points your query is going to return. In a lot of UIs, and in earlier versions of Grafana, those two things would be unaligned. And this makes it really hard to cache the results, because basically every time you refresh the page, you'll get subtly different results. Modern versions of Grafana will align them in the client side, and so this is a no-op. But just for backwards compatibility, we add this little alignment in here, and it massively increases the cacheability. The next step we add is we split the queries up. We split them up by day. This is configurable, but the most effective we've found is by day, because that actually aligns really nicely with how we shard our index.
So that means if you do a 30-day query, it splits into 30 individual queries.
Yeah, exactly, yeah. Now but the nice thing is you can execute those in parallel. Oh, before we do that, we then cache the results of the query at this step. This helps bound the size of the entries in the memcache for the query results, and generally means you don't have to do too much maths when you're kind of figuring out what bits are cached and what bits aren't cached. And it can cope with missing bits in the cache. You know, if you did a query here for an hour's worth of data and a query here for an hour's worth of data, you can fill it in the bit in the middle, and Cortex will figure out which bit needs to be computed and go and dispatch that. Then the final bit is we actually dispatch the queries out to the querier in parallel. So a 30-day query will do 30 subqueries. Some of them might get cached. Some of them might already have been calculated. The rest of them will get processed in parallel. In fact, we actually do a step more than that. They actually get put in a queue, and then we do kind of fair quality of service between tenants so that one tenant can't come along and do a 120-day query and kill another tenant who's just trying to do like little 1-hour queries. So there's a queue, and then we dispatch them.
Do not take that as a challenge.
I mean, yeah. I think there's still some work to be done on the quality of service.
On Tom's server, not on mine.
So, how good did this get? I mean, unfortunately, I didn't record methodically performance results from before we did all this work, but these are results from last week and our average query performance, and you can really see the effect of caching in these numbers. Our average query performance, which is basically when you hit the cache, is 50 milliseconds. I'm pretty happy with that number. 99, this is across our entire production fleet, which is involving some very large, very adversarial customers who luckily aren't in the room, is about 500 milliseconds. I think we've got a little bit more work to do, but I'm considering some of these queries give me a year's worth of data over 800,000 time series. I'm actually pretty proud of that number. So that's it. That's how we've optimized queries in Cortex. I think one last closing comment. Most talks about distributed time series databases seem to focus on the ingestion path. Every talk I've given about Cortex has talked about how ingestion is hard. And don't get me wrong, ingestion is really hard. But as Bryan said, we've been doing this project for about 3 years. And one of the things I'm really happy with and really proud of is the fact that we've kind of solved most of the problems we had, at least in the ingestion path. And we've got time to spend on optimizing the queries. And it's I think it's a good sign of the maturity of the project that we've got to spend so much time there.
Yeah. So we should say, repeat, it's an open source project. It's a CNCF sandbox project. We are very keen to get people involved. Please try it out. Please file bugs. Please file PRs to fix bugs. We have a Slack you can join, ask questions, join in. So with that, has anyone got any questions? I should run around with a mic. How did I get to be the one running around?
Lucked out. You can shout. We'll shout one and repeat it, shall we all? No?
You're the nearest. You weren't the first. But,
Perfect. So we started implementing Thanos, we paused it, and now I saw M3 and I saw Cortex, and I wonder when to choose which.
You want to ask me, the author of Cortex, which one you should choose?
Yeah.
I mean, I'm being recorded, so I'll be nice.
Okay.
You should choose Cortex.
All right.
Do you want to add anything to that, Brian?
Okay, fine.
Yeah, so they're solving the same problem, but with very different engineering trade-offs. M3, they wrote their own database. They didn't hear that piece of advice. Thanos, really the similarities are greater than the differences with Cortex, but Thanos, the latest data is at the leaf. Any query which is up to date is hitting all the Prometheus servers. Cortex brings the data centrally. So there's quite a big philosophical difference, and also the multi-tenancy. Those particular things, the fact that all the data is owned and stored centrally, and multi-tenancy, separating one set of people from another, those features certainly appeal in certain cases. If those aren't your cases, I don't know. Yeah, there's different engineering trade-offs. That's as far as I'd go.
Another question. Yeah, chap at the back. I think you were first. I'd just add to the Thanos v Cortex debate. Thanos got easy to use. They got it right from day zero.
Yeah. So first of all, I also like lasers. Those are nice. Second, we actually started using Cortex a little bit, but then it didn't quite work, so we started using the hosted version from Grafana, and it works really well. But we just get like these random 4-2-1s and like weird.
What's a 4-2-1?
I think too many requests.
Okay, we have rate limiting.
4-9.
We have rate limiting on queries, and we have rate limiting on writes as well. I mean, not a pitch, but talk to one of our support reps. We can raise your rate limit.
Oh, it's rate limited.
We have a lot of clients. And
there are other. Okay. Anyways, but so if we want to run our own, because we might want to run them, like for example, on Bigtable, on top of Bigtable, or on a replicated GCS bucket. So we might want to run our own. Is that like just plug and play from there? And is there a migration path?
It's getting more plug and play. The work we did in the lead up to KubeCon to enable that demo, to make it much easier to spin up a Cortex cluster, is all about helping people who aren't Brian and I start their own Cortex clusters. So there's now a doc to show you how to get started. There's now example config. We're going to be working hard over the next weeks and months to document more and more and make it easier to do this.
Yeah. When we started, we just extrapolated it from the code.
Yeah.
Yeah. That's a little bit hard.
Cortex used to, 2 years ago, 3 years ago, it had no docs. Yeah. So we're trying hard to be better. But also, like, if you've learned anything from running it, a good way to get involved with the project is to contribute docs. And so, if you've found anything incorrect or found anything that's not documented, like, write it down and we'll merge that, really quickly.
Yeah, that's true. Thank you.
Brian.
Other hosted Cortex, other hosted Prometheus as a service are available.
Yes, of course.
But when you're like open on the internet to absolutely anyone who wants to show up, and I'm trying to get to you, but I thought there was like an aisle down the middle, or this is just not happening, is it? Let me just finish my point. We're kind of open on the internet to anyone who wants to throw any kind of socket at us, and so yes, you have to put rate limiters in, you have to put protection at many levels, and those levels are configurable. Cortex is per tenant configurable on all the limits, so it's a fact of life. Yeah. Okay, go ahead.
Hi, I was wondering how aligned with PromQL specification are you? I mean, there has been the release of subqueries recently. It was maybe 6 months ago. Do you support that right now?
Yeah, so do you want to answer? I can't remember. Okay, so we're up to date. We try and stay up to date with the latest release of Prometheus. We just vendor the same code. So it's not as if we have our own implementation of PromQL. We just, so we're up to date is the short answer. If you ever find a way we're not up to date, then file a bug, and it just means we need to update our vendor. We do it quite proactively, though. The ones you reference about subqueries, There was a bug, and we fixed it.
Okay.
So,
okay. And another one, are you using the same code for the function? For example, there's an extrapolation in the rate function, the delta function of Prometheus. Are you using the same code? Are you doing the same extrapolation?
We literally vendor the Prometheus query engine, parser, and execution. Even like the chunk compression that Bryan alluded to is from the Prometheus code base as well. Like we've effectively taken Prometheus, broke it up into little bits, and added our own glue between them to do all the distributed systems work. But we only get one question, so. Right, last one now, so choose wisely, Bryan. Last one, go on, one more.
We got time for 2 more.
Okay, 2 more, yeah, you're the boss.
So let me go all the way over here first.
I tried to take this off to give it to Bryan, and now I have to hold it.
Okay, hi. For instance, if we want to have globally distributed Prometheus and push data into Cortex, what would you advise if it's like easy as like pushing data, or should we do something else special?
Yeah, just do it.
Yeah.
I mean, well, so you in terms of can both ends of the wire handle high latency? Yes. The Prometheus sending side will shard the sending channel so to cope with the fact that you might have like a 200 millisecond round trip time or something like that. So that'll work fine. On the receiving side, there might be a question about whether you care about replicating your data geographically. That we punt to the DynamoDBs and the big tables and so on. So yeah, just party on, geographically distribute the heck out of it.
It's up to you. One more. What do you reckon? One more?
Yeah.
One more. Go on. You choose quickly.
Yeah, I guess I'm closer. So it looks like the big advantage of Cortex over alternatives is the multi-tenancy. Could you explain a bit more how does it work, and especially from the API Cortex or Prometheus API perspective?
So the easiest way to explain it is on the way in, when you're sending data, you have to provide an extra HTTP header that says what tenant it's for. And then on the way out, when you're doing queries, you have to provide the same header. And then every single data structure, every index, every storage system within Cortex is keyed by that thing you provide. And it can be anything. Like the point I think you made, sorry, I've got the mic, so. The point you made that I thought was really good in the last talk was there's no API to Cortex to create a new tenant. Like tenant data structures are created on demand. So if data comes in for tenant 1 and we don't have an in-memory data structure for it, we just create it. This also means that any kind of authentication and authorization is out of the scope of Cortex. The expectation is you'll stick an Nginx to do HTTP basic in front of it. And then put that HTTP basic in your remote write path from Prometheus to do authentication.
Okay. Any plans to support that natively in Prometheus, like remote write API or in Grafana, like setting the header? No, not really. No, you can also, with the recent changes, you can turn it all off as well, which has made that demo possible. So that demo wasn't multi-tenant, it was single tenant. Anyway, we're out of time now, so thank you very much, everybody.